Everybody, welcome. Thank you so much for coming to our first virtual town hall for the Apache Cassandra community. And without further ado, why don't we turn it over to John Haddad? He is talking today about Cassandra performance tuning like you've been doing it for 10 years. He's very well known for knowing how to do Cassandra really well. We're excited to have him here. John will be presenting. So we will get going with his presentation right now. John, if you need anything else, just let us know.
All right. Thanks, Melissa. Appreciate the intro. So I am John. I've spent around 20 years in tech, 10 of which I've been fortunate enough to work with Cassandra. It's been a ton of fun. So I got started with Cassandra 10 years ago, working at this startup in Santa Monica, and we had a scalability problem. And they worked with MongoDB and a bunch of other stuff, and I brought in Cassandra, and it turned out to be a great decision. So I got involved in the community and then eventually moved to DataStax, which was kind of a no-brainer if you're really into Cassandra. I spent a few years there working with Patrick and a bunch of other amazing people. Went on to be a consultant at The Last Pickle, which was incredible experience. I got to work on do performance tuning for at least 100 different clusters. Moved on to Apple, where I helped out with the 4.0 release, which is pretty awesome. We built some really cool tooling to help testing there. And then I moved to Netflix. So that's where I just left. Netflix, I did a lot of the performance tuning for the Cassandra clusters, for the biggest clusters that we had, things in the streaming path, things of that nature. And now I'm on my own. So now I'm doing consulting again on my own. Available to help out with people, available to help people do this sort of thing all the time now. Now, when we start talking about performance tuning, one of the most important things is to have a methodology. Otherwise, we're just turning dials and hoping things go right. And randomly picking things and changing them rarely gives us better results. So it's very, very important that we have something that we follow, we stick to it, and it's practical. And I got introduced to this idea while I was at The Last Pickle. It was invented at the Air Force. It's called the OODA loop. And the OODA loop is designed to basically help you perform well and make tactical decisions in short amounts of time. And so the idea is that we have the first stage, which is observe. Observe, you're basically taking in information. And then orient, and during the orientation phase, that's when you take the information that you've learned and you build a mental model and you try and understand what's really happening in a scenario or in a system. And then you make your decision on what you're going to do, you act on that decision, and then you start the loop over, you go back to observe. And you basically just keep going around the loop until you achieve either the best results you can or satisfactory results. Now, typically, when we start talking about performance, people think of things like dashboards, which are incredibly helpful for understanding kind of a long view of the performance of things. You can see here numbers are going up and down. Very, very helpful, super important. And when things go wrong in a system, we tend to want to also see logs. So the combination of high quality dashboards and logs are what we rely on to get a big picture understanding of the state of a system. But when you start doing performance tuning, you kind of want a little bit more feedback, because in a lot of systems with, let's say, dashboards, you might find that you might have only refresh your metrics every few minutes, or, best case scenario, it's every, let's say, 15, 30 seconds or something like that. So you're not getting real-time information. So I like to rely on command line tools for a handful of reasons. One is I like the real-time aspect. And two, I really like the fact that I'm able to tap into some of the underlying metrics in the Linux kernel in order to understand what's happening with my hardware. And when it comes time to do performance tuning, understanding your hardware is incredibly important. If you don't understand what your hardware is capable of doing, then and what it is doing, then again, you're just turning random dials. So there's a really, really good technique called the use method. And this was developed by Brendan Gregg. And this is a really great way of understanding any piece of any hardware in your system. And it's also really helpful in understanding like internal software queues. So things like how many requests are coming in you can model that Cassandra side of things, but it's really, really helpful in understanding your hardware. So this stands for utilization, saturation, and error rate. So utilization will be, I'm using, let's say, 50% of my CPU. Saturation is if we've fully utilized the CPU, what's the queue look like? Do we have too much work for the piece of hardware to handle? And is there now a queue behind it? And error rate. Error rate is super important because it doesn't matter if we get really great performance of 1 millisecond for every query. If 100% of them error out, it really doesn't matter at that point. So we need to understand these three things in order to truly know what kind of cost we're seeing on our hardware. Now, before you even get into doing performance tuning, it's a really, really good idea to benchmark your systems and to understand what they're capable of. And this is where I use FIO. So most of the time, or a lot of the time, one of the biggest limiting factors when it comes to a database is going to be your disk, right? And this is true especially for drives that are attached to a network where they might have longer latency. It's spinning Rust is definitely, you want to know what the limits are there. And fortunately, we're not really seeing a lot of that anymore. But solid state drives still have pretty significant limitations. And even when you get into NVMe drives, when they can push 2 gigs a second at 100 microseconds P99 latency, you still have limits there. And I've seen misconfigured servers behave poorly even with NVMe drives installed. So I highly recommend taking a look at FIO before you even pick your hardware or after you pick your hardware to benchmark it. And then that way you can set up your alerts, you can set up thresholds appropriately. So this is what FIO looks like. There's a ton of text on the screen. I hope hope you can read it. The thing that's really important here is that it's a configuration-driven tool. It's pretty easy to use, and you can simulate virtually any workload. So this is actually simulating a bunch of random I/O mixed with a bunch of sequential readers and writers, effectively simulating Cassandra's read operations and compaction at the same time. And so if you take a look here, what you can see is that my writes, I'm doing 27,000 IOPS. My bandwidth is 800 megs a second. And if you look down where it says CLAT percentiles, you can see 99 percentiles, 55 microseconds. So this was on my laptop. It's got an NVMe drive. It's really fast. It's awesome. So I know that my laptop can do all sorts of really cool stuff. I recommend using this if you're going to deploy in the cloud. Very, very helpful to understand what your disks are capable of. So once you know what your disks can do, then you can actually move on to the side of things where you start doing performance tuning. Now, it's really helpful to have a good high-level understanding of what your system is doing at any given moment in time, especially before you start making changes. And this is where I like to rely on tools like MPStat. There's a few other tools that are available that can give you similar information. IOStat is really useful and has a high overlap with this. Even a tool like Top can tell you a lot of the same information. This just happens to be what I like to use because it breaks things out. You can have it break out by CPU, and you can see how much time is being spent in user. Now that's like your Java process. You can see where it's being spent in sys, so that's in the kernel, and you can see where IO wait is happening. So it's nice to see that broken out. If you see a high level of IO wait, then you can determine that your disks are not performing that your disks are a bottleneck. Once you've taken a look at MPStat or these other high-level tools, you might start to ask yourself, what is my database doing? And that's where I'd like to introduce flame graphs. Flame graphs are a really great tool invented by Brendan Gregg that takes sample profiling and mixes that with an incredible visualization that makes it really easy to understand where your time is spent. So if you take a look at the graph right here, as you go up, it's going up the different levels of the software stack that you're running, and the width is a representation of time. So it's very, very easy whenever you open up one of these graphs to get an idea of where your time is being spent because it's just the wide blocks. I've used this to diagnose a lot more than just Cassandra problems. I don't know if any of you have ever been working on someone's come to you with say, hey, the database is really slow. And you look and it doesn't look like it is, and then you profile, and then you look at the application, everybody points to each other. This is a really nice way of getting to the bottom of issues very, very quickly. So highly recommend setting this up and taking frequent profiles with it. Now, I talked a little bit about disk being the problem, and that's what I'm going to focus on for the next few slides here, because I don't have all the time in the world, unfortunately. I'd love to talk more about this stuff. But today we're going to focus on disks because more often than not, it's the root of the problem when you have high latency. And it's the thing that you want to make sure that you tune most appropriately because it's the slowest part of your system. So this slide is talking about BCC tools. BCC tools tap into Linux perf events, which is internal counters in the kernel. And what it does is allows you to very quickly, with low overhead, get a lot of really interesting information out of the kernel about what your system is doing. And so I just stole this diagram from the BCC tool site, but it shows you all of the different things that are available to understand, like the different components of your system. You can look at what's happening on your network. You can look at your file systems. You can look at virtual memory. Everything is available to you. Now, I've worked in a lot of problems where the question has been, where is the performance bottleneck? What do we have to do in order to improve things? And this is where I've heavily relied on in the last few years, this tool. It's called bio-latency. Stands for block IO latency. And the really cool thing about this is you can run it across one drive or multiple drives, and it outputs something like this. So you can put in a interval, so it will monitor your drive, or you monitor your drives for some amount of time, and then it will output this histogram. And what's really cool about this is you can see a histogram of the distribution of the request time, and it makes it really obvious like what's going on and where your time is being spent. There's a few other tools like bio-latency. There's bio-lat percentiles, there's bio-snoop, there's bio-top. So I really recommend taking a look at BCC tools to understand these things. The main goal here, though, is to understand if you see that your latency in Cassandra is at let's say it's 10 milliseconds, and you're doing some number of SS tables per read, well, you want to know how expensive is it to actually go to disk? How often is that happening? And by using a tool like bio-latency, you can get a very, very good understanding of what's actually happening at the device level. Right? And then we move on. There's another really great tool in this library called XFS Slower. Now, there's a whole bunch of different versions of this tool. There's one for ZFS, there's one for BTRFS, AXT4, like pretty much anything that you can think of, you're going to be able to find a corresponding tool for. The really cool thing about this tool is that it works at the file system level. So I recently worked on a problem where we were concerned about the performance of a file system because the team had network attached storage. And when we ran this, what we found was that we were seeing very, very high latency when the commit log was syncing, but nowhere else. And it was through that we were able to determine that the cost of syncing the commit log was actually the heaviest aspect of what they were doing on the IO side. And that's because the writes, as they were coming through, had to be written to multiple drives, had to be written over the network, and F-syncing on that side. On the other side, we had to wait for that. So, and reads were able to be served at the cache. So it turned out that in this file system, reads were actually quite fast. We never saw them show up in this list, and it was only commit log syncing. So you can pass here an amount of time. So by default, it's going to show you 10 milliseconds. What's really cool about this is it tells you the type of operation, process that did the read, the file, and how big the read was, and the offset in kilobytes, and the latency. So it's an incredibly powerful tool. So if you're curious as to what's taking a long time after you look at bio latency, fire up XFS Slower, and you'll get a much better idea of what's actually taking time on your system. You'll also know how big your reads are, which is really, really important. And then lastly, the third tool that I'm going to talk about today is called Cache Stab. Now, this is really interesting. So Cassandra, because it relies so heavily on the page cache, it's incredibly helpful to know what your cache is actually doing. And one of the big problems here is, for example, if you're trying to figure out how much memory to allocate to the JVM, one of the things that people will tell you is don't put too much, because you want as much memory to be available to the page cache as possible. Well, CacheStat will actually give you a really good understanding of the effectiveness of that cache. So if you increase your memory to the JVM, you can see through CacheStat whether or not your page cache hit rate is up or down or the same. So in this case, you can see most of the time our hit ratio is staying the same, and then all of a sudden we have a ton of misses. So this is helpful. I like to give Cassandra quite a bit of memory. I tend to just recommend throwing 30 gigs of memory if you can afford it at it. But a lot of the times that this could come at a cost. So if you had, let's say, 64 gigs of RAM, increasing that memory going from, let's say, 20 to 30, that can take a lot of memory away from page cache. And so if you're not sure whether or not that's the right thing to do because of the negative effects on page cache, this is the way to do it. And you'll get a readout right away. And as the system is running, you'll be able to tell whether or not your page cache is effective. Now, I assume that a few people are here for some easy wins. And I can tell you a couple that are pretty helpful. And I have found that even in pretty much across almost every environment I've ever looked at, these have had an impact and these have been relevant. So the first one is read ahead. And read ahead is a really interesting idea. The idea here is that if we have high latency drives and we do a request, we want to read more than what the original request is. So let's say we ask for 4 bytes off the drive. Read ahead is going to go and by default pull 128K off the drive. Now, that's really helpful when your drives are high latency and the cost to going back and reading continuous tiny bits of data is going to be really slow. But it can be really problematic if you only actually want a little bit of data and you're not doing sequential reads. And this is the case with solid state drives, it's the case with NVMe drives. So a lot of the time, what actually ends up happening is people use the default read ahead on your system. You can go ahead and check it with block dev. It'll be get RA. This is to change read ahead. When it's doing read ahead, it increases what's called read amplification. So what you end up doing is just a ton of throughput on your drive. You end up oversaturating it, and then everything ends up being slow. And I've seen this happen even with NVMe drives, where a team had set their disks to have multi-megabyte read aheads. So every request would do multiple megs of reads, and they fully utilized the NVMe drive, which is kind of crazy. And they were seeing 200 millisecond P99 latency. And fixing this brought our latency down to about 3 milliseconds. So this is a really, really big deal. And on the same idea as talking about read amplification, we have compression. So compression was recently changed in, I'm not sure if it was 4.0 or 4.1, but originally, or for the longest time, compression, which is a table level parameter specified by this flat, the stanza at the bottom here, where it says compression equals chunk length in KB 64. That 64 is the size of the buffer that's filled up with data, compressed and then written to disk along with some metadata. Now, the interesting thing about this is when you need to do a read, you have to get this whole block off disk. You have to do the entire, you have to get all the original data into that 64 kilobyte block. Now imagine a scenario, again, when you're only reading a few bytes or 1K, 100 bytes, something like that, you end up, the read amplification issue hits again, because now you're reading this huge thing off disk and you're only using a tiny bit of it. And so fixing compression, sizing compression to be smaller for read-heavy workloads or read before write workloads can show a humongous improvement in performance. And I realize it's just saying read-heavy. You might think I don't have a read-heavy workload, but there are 2 workloads that are actually read-heavy in disguise, and those are lightweight transactions and counters. So in the case where you're using lightweight transactions or counters, if you change your read ahead down to about 4 or 8, depending on the or 8 KB, depending on what you want to get out of the rest of the system. And then you size your table's compression correctly down to either 4 or 8K, you can actually see a 10x improvement in throughput and latency. All right. And that can translate directly to a 10x reduction in cost for your cluster. So this is a huge deal. And this is something, like I said, I've seen this pretty much everywhere. And every team, almost every team, no matter how experienced, has had this problem. And it's the easiest thing to tune. I hope you go ahead and try it out and see some improvement on it, because it's a total game changer for Cassandra. So hopefully that was helpful. I'll definitely be answering questions in Discord. So please feel free to ask, and I'll turn it back to you, Melissa.
Thank you all for joining. We really appreciate it. And if you have a use case or case study you'd like to share, you can get in touch with us via the Meetup page, or we're on the ASF Slack or the Cassandra Discord. My name is Melissa Logan. You can find me there. Please reach out and let us know if you'd like to present.